Alright, welcome again. I'm also recording. We are into our 6th session. We've had other sessions, but 6th lecture. We will be meeting on Tuesdays also and Saturdays from now on. This is to expedite the completion of the module by Christmas. Everybody appreciate that. We're supposed to be doing a total of 13 sessions. We have gone about 8 sessions or 7 sessions. 8 sessions. I kind of include the consultation as sessions. Okay. So this will be the 6th lecture. We've had 2 consultations. So we've had one, the presentation session. It's 9 already. So we have 4 left, and based on the normal scheduling rules, Richard or insert. Mute from me, insert. Mute from me. Yeah. So, yeah, we have 4 sessions left officially, or based on quality assurance requirements. I don't want to shortchange what the standard is. Yeah, we should be able to complete what we need to do. Your final project or presentations will not be one of those 4, because that would be categorized as an exam session, which is going to be after the 4 remaining. Alright. Brandy's house will be finished by the 15th. Well, today is the 1st, and I said we have Tuesday and Saturday. That's 2 weeks. 4 means 2 weeks, right? So the 15th would be a Tuesday. A Saturday, since today is the 1st. So the 8th and then the 15th. Yes, one, you'll be on vacation. But I hope wherever you're on vacation, there's still internet there. Oh boy. That is the beauties of distance learning, not true? Anyway, we should be finished with all lectures on the 15th of December. That's 4 more sessions after this. Okay, so we have a session on the Tuesday coming, which would be the, let me just check my scheduling, the 4th, and then the 8th, and then the 11th, and then the 15th. Alright? And then you have your last presentation, which I'm going to give you the choice to decide when you would do that. Also, by Monday I'll post the specific requirements of that presentation. Alright? So the 4th, the 8th, the 11th, the 15th are the last 4 sessions. And then the presentation after that. You can make the presentation anytime you want. If you want it to be 1st of January or on Christmas Day, it is not my business. Alright? Everybody understand? Hello?
Yes. January sound good, man.
Alright, let me put a little limit. Not past January 15th.
That's alright.
not past January 15. Or put it this way, not before the new semester of school starts. Coming out on a time. Yeah. Still deal with this one. We start a new semester. Alright? Any questions? Everything is clear. Good. Yeah, good afternoon. Good evening, Devon. I haven't started content of the session yet, just doing some announcements and preliminaries. Oops, audio in and out. I think it's because I'm talking soft. What percentage of the final grade is the project? I did explain that. Let's go over it again. Hold on. I'm pulling up the details. Alright, Shanara? Okay, so the course is broken down as follows. We'll have to post it on the website also. Hold on a minute, yeah. There is an element called final, which would have been 40%. Instead of giving you a final, I said we would do 30% of that would be actually the project, the final or part 2 of the project, and 10% would be an assignment. Hold on, still trying to pull up the information. Right. So your first project was 20%. Your assignments will together be 40%. All right. And the project, the final project will be 40%. Alright, let's say that again. The first project was 20. First project is 20. Your assignments will be 40. You have 2 more assignments. Assignments will be 40. and your final exam or project is going to be 40. Everybody clear?
Clear as day.
Oh. Yeah, man, we're going to get to the feedback. That will be the start of the lecture. Insert you again. I go permanently mute you, no boy. Are you such a quiet young man? Are you such a quiet young man otherwise, eh? All the people. Alright, let's get to our discussion on the lecture. Hold on a minute there. Our discussion on the first project. I'm just going to speak to content and some administrative matters regarding it. Firstly, I'm going to quickly summarize the five presentations. What I would have looked for more, and what you can sort of address in your projects if possible, and if you can't address it, you would kind of defend why you can't address it in the project, okay, in your report. First, environmental resources. I'm just going to go in the order as presented. Okay, for everybody, first of all, for part 2, part of your grading will be you're sticking to the time. So I'm not going to stop anybody in a presentation. It causes me to suffer, and it causes everybody else to suffer to sit through the whole thing. If you go over, I'm not going to stop anybody, but it will become a part of your final grade, and the rubric will identify how going over the time or sticking to the time will impact the grade. Alright, it is just part of being a master student in terms of learning presentation or mastering presentation skills. If you're given a certain amount of time and somebody says, you know, if your boss say I need you to present something at a meeting and you only have X number of minutes to do it, and this is what the boss say he want you to talk on, and you think, boy, you know, look like me have enough time. That's what you're given. You have to find a way to use that time. If you don't use the time, well, then you wouldn't have achieved one of the objectives of that presentation. Alright, so yeah, the longer you go over the time, the greater your infraction. So persons who stick to the time will get full marks on the time part of your grade, and or probably I would say it another way, you will your grade won't be negatively, yeah, you'll get a better mark or high marks of sticking to it. And as you go over, let's say 5 minutes over, up to 5 minutes over, or it's going to be probably like up to 2 minutes over, up to 5 minutes over, up to 10 minutes over, your grade will go down the longer you stay. Fair enough? Again, this is not engineering analysis, this is just masters. Indeed, eventually every single module, the plan is every single module that you do is going to involve presentations, reports, case studies and such. Well, not you, but future cohorts, and even you, some of you will have to deal with quite a bit of that, and so we're going to be really strict about that, because we want, by the time you finish the year and a half, you would have done so many presentations, you would have become competent in delivering yourself and delivering technical information to lay as well as technical personnel. You have to know how to do that properly. Alright? Everybody clear on that? That's a general statement I'm making. Alright. Okay, so let's speak to each presentation. First, environmental resources. I recall that just quickly you discussed a general history of numerical methods. Didn't see much as to the use of numerical analysis in environmental resource management or environmental resource engineering. It was more a general thing. So I would have wanted a little bit more focus. Is there a history in environmental resources? Is that clear? Oh, by the way, I'm not a very negative man, you know, but I just want to get to the point. So before I flatter you guys, just want to get to the point. Alright. Next on that matter, everybody is pretty good enough, so I don't want you to think that my negative statements like, boy, I may get a bad grade. I just trying to tell you what you need to improve on your score. So next, so you discuss MATLAB and R, it was, right? As the two right resources. I was curious, is it that, was there no software out there that you found that actually was geared toward environmental resource or environmental systems or such? Just a general question. And if there is, please also speak to those. Understand? It may be a weak software, but whatever is there, speak to it. What if, okay. Brandis, you understand what I'm saying too? Now if you can't find it, let me know you can't find it. But remember, that's part of this. The objective is to see that. Alright? Good with the time, I'll just say that much. Alright? And I was quite impressed with R. Didn't know R, didn't know of R. I think I'm going to like to learn about a little bit more about R. Anyway, moving on. Chemical processes. That was hold on. So chemical process engineering, they used, it was ChemCAD, was it? Let's see, Richard, you're here, right? Some of these things are by memory. Here, my other computer that I had this information.
Yes.
Yeah, my other computer.
Yes, it was chemical.
And the what was the open software again?
Open form, and we also spoke about Octave.
Yeah, man. So again, so open. What was it? Open what again? Not the Octave, the other one.
Open form.
FOAM. That was a specific chemical software. FOAM.
Right.
Yeah. So you know you guys were a bit more challenged at the time. I do know you recall that. So you have to work on that element. Appreciated it though in terms of the information that you delivered. Demonstrations were good. Work on the time. Also on the matter of the history. I think you did similar to environmental guys where you just spoke generally. Understand what I'm saying?
Sir, I think it has to do with the way question 1 objective was presented or it was stated.
Yeah, that might have been. So right now I'm if it was misunderstood, I'm clarifying that now.
Yeah, man.
Anyway, so guys from chem processes understand what I'm saying?
So you're saying that we should include how numerical analysis was used before computing?
No, how numerical analysis is used in the field of study that you are responsible for doing research on. Historically. Or historically, how has analysis been done in the field that you're doing research on? Understand what I'm saying? Insert you again. Mute again.
Yes, you had said that you weren't sure if we would know how that would be used.
How what?
Software.
How what would be used?
Numerical analysis.
No, what I'm saying is look into, consider how numerical analysis has been used in the field of study you are responsible for studying. So you're doing chemical processes. Historically, how has it been analyzed numerically? When were certain software packages adopted to assist in it and so forth? Just for chem processes. Not just for it, you guys spoke to the general use of numerical methods, which is quite fine. No problem. But I'm saying, since your responsibility is also chemical processes, then you would also speak to that. Alright?
Okay.
You understand the answer?
Yes, I do.
Okay. Hold on. I like a call coming in. Please discuss among yourselves. You can let me hear while I go on. I'm going to mute myself briefly, okay? Yes.
Hey, Jam.
Alright, no worry about it. Let me I'll call back that person. So some people interpreted it the way I did. I'd say no. Alright, let me do the electrical circuits. So for electrical circuits, this isn't the same order that let me go back to the actual order that I use. Hold on a minute there. structural analysis should have been next. Alright, well, so structural analysis, those guys were more okay, good. So that was Dwight, Devon, Jordan, Edward, right? You guys here? You guys here?
That's right.
By the way, hold on. Yeah, so for that job, pretty sound. Yeah, pretty sound in terms of your use of the two software packages. I'll go back to the environmental. It wasn't environmental, that was urban planning. They're the ones that did SWIM, right? The SWIM software. PC Swim and EPA Swim, right?
Yes, sir.
Okay, let me speak to you guys first. So you probably were more dead on in what I was thinking. Your history mostly focused on those two, on that field of study, and also you're very timely, so commendable. I just want to let you and Cleos know that. All right, and I think everybody else here
Thank you, sir.
can agree that your presentation was pretty smooth. So we have to give credit to where credit's due. All right. Others, you're free to chime in and say, I true, then do it. Oh boy. Alright. I just reviewing little things just to make sure that I get everything right. So hold on a minute. Another matter, for your submissions, before I go much further, for your submissions, only one group so far submitted their presentation. Only one group. Please record the presentation should have been submitted. Everybody remember that?
I thought it was big and submitted the reports.
No. Because it's not something that you would change. The presentation is a presentation. What you presented. Let me go back to the assignment. Let me read it just so I am not saying something wrong. It says deliverables.
Richard. Sorry.
Hold on. You know, say that me right. Same thing what you said a while ago. Exactly that me right. But the report should have been after. Well, I think everybody's clear. The report should have been submitted after the presentation. That's what I said to you guys, but then I realized what I wrote wasn't that. I had the report at the same time, or I have the report before the presentation, which wouldn't have been correct. Alright, let me deal with electrical. That's Kevoy, Bedard, Franklin, was it? And hold on. Franklin and who's the other person again? Okay, so nice, pretty good also in terms of laying out the history. Definitely the two software are, you know, dead on. The demonstration was a little simplistic, you know, the output being 5. I think it was something like that. So that was a little simplistic, boy. You hearing me?
Yes, sir, I agree.
Okay, good. Oh, so Brandis is now saying she couldn't find anything specific to environmental, right? Alright. I may help you and find something to get you started. That sounds like more work, not sure. Don't mind. Alright. But apart from that, again, the time, I think you guys weren't so bad with the time. Weren't so bad, but the best with the time were the first group, and that's the environmental resources and the urban planning. They were quite good with use of time. Alright. Other groups are a bit weak, you know yourselves. Alright. Who may not comment on it? Who don't comment on it? Hello?
Hello, sir.
Yeah, man, I talked on electrical already.
Structural.
Oh, structural.
I just reached.
Oh, yeah, man, I spoke on structural briefly. Jordan. Yeah, you guys did good. Your time was kind of long. So you got to work on the time part, alright? I was also saying I made an error.
Alright, thanks, sir.
Yeah, man. I made an error. You can speak to your other group mates regarding the other comments, general comments that I made and the requirements, what I want of you. Please submit your presentations to me as soon as possible. The ones that you did do. Don't modify it or anything like that. Alright? Here I had some error in when it's really the report that was supposed to be submitted after the presentation. Okay? So it should have been the report, the presentation, the abstract first, then the report, then the presentation, and then the soft copy of the presentation, and then the soft copy of the report. So it's the abstract, the presentation, then the abstract, the presentation with a soft copy of the presentation, and then the report afterwards. So what I'm asking you to do, everybody, as soon as possible, before even the session is done, or as soon as the session is done, please just upload your presentations to me. Okay? Oh, last thing now. It is quite good that everybody made sure you played your part in your presentations. However, it is still one presentation. Group work, that all being group work, it's one presentation that you all should do. Therefore, your presentation template, your slides must be consistent. Alright? So I do realize each person was tasked to do a section of the presentation, and then you just kind of pull them together. So you should have a coordinator when you do presentations like that to ensure a consistency of format. Am I clear? Yes, slides should have the same theme, but also you should work on having the same, not just theme, but style of delivery. I know everybody have their own style, you know, but like when one person is very points and then the other person is very paragraphy on your slides, it makes the presentation a little disjointed. Understood? So everybody is asked to ensure that when you work together as a group, I have to do a group presentation, which is common even in the professional world. You must ensure a consistency of a presentation. It's like edited books. You have, sometimes there are texts or even publications, magazines, whatever, where many people contribute to it, but the whole thing is still one theme. So the editor is there to ensure that the style is consistent. Alright? So you have to ask yourself, who among you is the best in language or whatever, and document preparation and so forth. That's the person who will do that. That person is not supposed to put the content there. The person is just supposed to format it. Alright? And also to advise the presenter, each presenter, on how to present his part. Okay? So I don't want to know if you say, boy, that guy is doing the presentation at a theme style. I don't know, everybody kind of work with it, and I might not really feel comfortable with how it's done, but just make him go on, because you know you don't want to offend the guy. You're a group, and everybody could get licked if one person doesn't do it properly. Alright? You work together. Yeah, man, you have to war a little bit. Yes, one, that's why I go. You have to war a little bit. And I really worry, what have to learn for you. You have to be mature, you understand? Don't just say that man they make him do film part and another man do film part and you not go say nothing. You know, and I really say go. Part of the master's course or study is leadership. That's not a bachelor's requirement, but that's a master's requirement. Alright? And communication. Leadership and communication. Cool? Everybody clear? That said, still, don't fix your presentations. I'm not going to penalize you. It's good for you to see a before and after of your growth in the program. So Don't try and fix nothing. Send it to me as is. But you have another presentation. You can show yourselves to have grown in that respect. Okay? And as I've said, I'll give you the time to put in. Not past January 15, but I'll give you the time to put in to ensure that you do it properly. Okay? Alright.
Repeat that, sir. Past. Where? Come again.
Yeah, Jordan, the guys will tell you all of those details about the presentation, the final presentation. Like when you come in late, you kind of miss that. Aye?
Yes, sir.
Cool. I want to continue now, so we're going to go into our topic, continuing iteration and moving into the next topic. Alright? So, here's where we are. Nobody should be seeing the whiteboard. Last thing we were dealing with was fixed point iteration, and so we did, this is the Babylonian method we talked to. Everybody should remember what fixed point iteration is. It's really coming out of a strategy in which, oops, I have to move this. Hold on a minute there. Hold on one little minute there. Alright, so what this does is it says when you have a certain function and you want to solve it, let me imagine I have a function, for example, x squared plus natural log of x equals 0, and I want to solve for that. If I try to solve it in this form, I could say f of x is x squared plus natural log x, and if I try to find what x for f of x equals 0, this solution procedure is called root finding. Okay, but the alternative would be if I had solved for one of these. I could, for example, say x equal negative natural log of x square root, for example, and we call this g of x. And if to solve for this using this as the function of interest, g of x being that, we want to find when g of x is equal back to x, we call this fixed point. And really all it is this function has its own plot. Let's say we have our plot y, x, and let's say this is the function. That's the g of x function. No, that can't be a function. Anybody know why that can't be a function? See who remembers their math. Anybody can tell me why this can't be a function? Nobody? Why can't this be a function?
Why g of x equals the root of minus ln x?
No man, I'm not saying why it can't be this function, but why is this graph here, this line that I drew here, why is it not likely to be a function?
A strong relationship does not exist between y and x.
Why you say a strong, what do you mean by a strong relationship?
Because a function is defined by the relationship that it has between variables, right?
Yeah. You don't
that just look arbitrary, I guess. I don't know.
Okay, you don't know, but I understand what you're saying. Anybody else? You're kind of on the right track, but not quite. Anybody else? Okay, in your computer there's something called, oh, Shanarai, you want to try telling me why what I just drew is not quite a function? It doesn't follow any law? Yeah man, there's a line here, that's a law. At this. Alright, let me show you. Go ahead. Go ahead, Julian.
Because you have no wait, you can't say.
You gone? Alright.
It looks like some x values might have multiple y's, corresponding y's.
Okay, that's correct. So as Franklin said, some x may have multiple y's. A function is something in which when you put in a value into the function, you get an answer. Okay? So for example, in Excel, you have functions, you know, like you could say cos, and then you put something there. It's going to give you an answer. Okay? If it doesn't give you an answer, it's not a function. Because a function should not give more than one answers. Understand? But you could have a case in which different inputs give the same answer. Okay? But you can't have an input giving more than one answer.
That's almost going. Let's say what Franklin said, but the part with the multiple inputs, I'm not sure what that part.
No, you can have more than one input giving back the same answer. For example, sine of 0 and sine of 180 degrees or pi give you the same answer, which is 0. Okay?
Or like a quadratic story where the two roots give you back 0. Could that be an example?
Alright, yeah, like the quadratics, the two roots give you back 0. If x equal that. But the point is, only one, when you put in an input, you only get back out one answer. It's more, Shana was saying something about law, and this is kind of how you can appreciate it. The way we say nature works is that when something happens, or when you have an input, it can't lead to multiple possibilities. It's only really one outcome that is possible. So where we are right now in time and space, there's only one path to this point, or to this state, or to this situation. Okay? So you could have had the exact same input in the past and end up with a different output in the future. Alright? So that's why this can't be a function. Kind of a divergence, but not quite. It's a very important mathematical principle. Alright? We'll go back. So let me erase it and make it look more like a function. So that might be more of a function. Okay? And this function will be the g of x. I want to also note, these are some little things that we've all been doing throughout maths, but we really are not clear on what we're doing, so I'm just saying some things as we go along. Next thing, you realize there's this thing called y, and you have this thing called g of x. Y is just an axis. X is a variable, but g is the function. Okay, what do I mean by that? I may call this h of x. These are different functions, and these functions give you a value for y. Okay, for example, for this x in this function gives me this y, but this x for this function gives me that y. Alright, so y is not the same thing as g of x. I hope everybody is clear on that. G of x is a function. Y is the output of the function. Okay, and another function can give you a different y. Alright, so on a plot where you have multiple functions on the plot, you can't label the axis by the function. You have to label the axis a generic variable like y, and each plot is labeled, and each plot is labeled as the function. The axis would not be labeled as a function. Am I clear? Is this kind of new knowledge, or I don't know this already? And that's a new knowledge. It's kind of old, but it's kind of supposed to be clarifying things.
Not new. I didn't know it's new.
You didn't know it. Good. Brandy said we should have known this. Did you know it, Brandy? What, Brandis? You did know this, or you did not know this? Okay, good. So clearly some people know that. Alright, continuing. So here we have a function. Fixed point just says when you write it this way, where x is oh, Devon asked me not to erase. Oh boy. Alright, Devon, I'll just make new slides, and I guess I'll try and save the presentation, or at least save those slides. Okay, so x equals g of x. So what we have here is another function. This function is y equal x, and so it's really what we're doing is we're finding where two functions meet. We're finding where, let's call one function hx equal x and gx equal minus natural log of x. So this is hx equal x. Let me make this one hx, right? And this one is g of x. Okay, this one is g of x, this one is h of x. And all I'm saying is I want to know when h of x is equal to g of x. Clearly that just means when x equal the square root of negative natural log. If you look at both of these together, then you want to know where do these two intersect. It just means this statement. Everybody clear on that? Alright, so that's what the fixed point is. Now there's a simple little rule we have in fixed point. Convergence occurs, and when convergence doesn't occur. It all has to do with the slope of g of x. If the slope of g of x is less than 1, 1 means, everybody should be clear, y equal x has a slope of dy dx equal 1. Everybody should know that, right? So that's the slope of this line. Now for this line, pardon me. Now for this line, the slope of this line, has to also be less than or equal to, I wouldn't even say equal to, it has to be less than 1 magnitude of the slope. If the magnitude of the slope is greater than 1, then the fixed point method will not converge on the answer. If the magnitude of the slope is less than 1, then the fixed point method will converge on the answer. Okay? That's the convergence test. Alright. Okay, so let's go back to slide convergence slide. Here we go. Alright, so, and I did some animations last week just to show that. Alright, okay, now the fixed point iteration was the first in a set of what we call open methods. Remember the difference between open and closed methods? Closed methods are ones in which you have a left and a right bound, or a minimum and a maximum x, and we know our answer is between those, and we are sure. And usually it's best to make sure you have one answer within your bound, and you must know that there's an answer there. You should always choose bounded methods if you are sure where your answer is, and if you are sure you only have one answer. Okay, always use bounded methods. Now and it's always best to make your bound as narrow as possible, as narrow as you know it to be. Alright, now the open methods, fixed point is the first one, and all the others, Newton, secant, and Mueller's, they are all root finding methods. Okay, so you have the fixed point method, and then the others are root finding methods, just as bisection is a root finding method, and regular falsi or false position is also a root finding method. Now those methods are based on they're open methods because you select one place to start rather than a bound. Okay, so let's first look at the Newton iteration. Sometimes it's called Newton-Raphson. I'll write it, Newton-Raphson, R-A-P-H-S-O-N, the Newton-Raphson method. Sometimes it's just called Newton. As I said, in almost every field of engineering, Newton is responsible for something, as well as maths. So the Newton, and you'll find him come up again later in this class. So the Newton-Raphson method, you actually again express your system in the root form, and you're going to determine the derivative of your system. So one requirement of Newton-Raphson then is that you must be able to determine the derivative of your function. Alright? As a function of x. Not every function you can determine the derivative. Let me just say that. It's not also always so clear. Just like how you can't explicitly solve for every function, in some cases you can't explicitly determine the derivative of the fixed point form of a function. So what does this mean? It means that sometimes, remember, you have several options in finding derivatives. So look at this case. Let's say you're doing a fixed point system, or sorry, a root, or you're doing the root. Remember, your f of x, or the function that you choose, you can put it in any form that you want. Remember that. So you can write the function. Remember, all that's required that the function is equal to 0. So you could write it any way you want. The point is this though, however you write it, make sure that you can find the derivative of it, of the function. Okay? Then next it says randomly. Of course, you really can't randomly do something like this. It should actually be a guess. And probably the guess is within a bound. So yes, it is called open method, but you do have to start somewhere. So you pick a value. We call that value the initial guess, or x0, and then from that you do this iterative procedure. And let's look at the iterative procedure. I'm just going to draw it on the whiteboard. I'll give you an example. Alright, so I want you to imagine here we have a function where, let me move the root a little bit higher, or the x-axis a little higher. Oops, sorry. That wasn't supposed to happen. Let's try it again. Okay, good. That's better. So hold on a minute, please. Yeah. So what we have here is, let's say this is our function. Alright, and I need to find and I know my answer is somewhere here. Okay, somewhere here. Let's say I guess this as my original x. What I do is I find the function value. This would be y equal f of x. Okay, I found the value for y for this x. Let me say x0. Okay, I also find the slope. The slope would be a line like that. Okay, having found the slope, what I do is I'm actually going to project a line from here in this direction. Oops, sorry. Hard to draw a line, just as bad as a whiteboard. Why does it have to go through 0? They don't want it to go through 0, but anyway, that's fine. So this is the line I'm projecting. I can use a ruler, you know. Let me use a ruler. Draw this thing on the meter. That's what I'm putting them to get the ruler for me. Hey, somebody carry a little ruler for me. Somebody carry a little ruler for me. A little ruler, plastic ruler. Huh? Yes, that's what I'm putting them to carry a ruler. Alright, so I'll be using a ruler. It will help quite a bit. Alright, so everybody's still with me though, right? Bear with me, bear with me, bear with me. I'm still learning to use these tablet things, you know? I think I'm getting better at this. Alright, I'm going to erase all of this and start again because I kind of figure out how to do this a little better. Come. Alright, so here we go. Nice. It's an actual ruler that I'm using. Pretty natural. Alright, and then the other line, let's go a little lower. There we go. Oops, hold on. Okay, there we go. Good. And then I'm going to now draw the function, change the color. It's a nice color there. Yeah. So here's our function. So that's our function, right? And then now we're going to start our iteration. So let's say I'm going to pick this as my original x. Okay, so here we go. So that becomes right here is my alright, so this value over here will be the function of x naught. Remember, that's the first guess, x naught, right? And what we want to do now, so we're going to project so we're going to project starting right here. Oops, hold on, that shouldn't have been. Let me fix that. Alright, so here we go, starting right here. This is the slope . The slope, everybody see this is the slope of the function, right? What I do, I'll project the slope so I project the slope there. Alright, so what happens is I use this becomes the slope here. We call that f prime at x naught. That's the slope. Alright, and based on that slope, this is now the estimate of where x1 is supposed to be.
Sir, can you repeat after you say f prime
no, x naught, or x initial x sub 0.
Okay, got it.
Got it? Then this now would be this would be x1. This is now our first x, or the first iteration step. And the truth is, immediately you're going to learn a lesson about all open methods. So here we go. This is now the function at x1. This is the function at x1. Alright? This is the slope at x1. And that slope will carry me to another estimate, which would be x2. And this value now would be the function, or I know I'm taking a little while, but just for you to be clear on how this thing go, let's take our time. Alright, this is a function at x2 right here, x2, and the slope at x2, it's a little steeper than it was at x0. So I'd say it's something like this, right? Everybody see this as the slope, and the slope would project to this value. This now would become x3. Alright? And then this is the slope at x3. Good. Or the value of the function at x3. Go across. This will be the function at x3. And the function of x3 has its own slope. Clearly. Clearly the slope here is about this. Everybody agree? Slope is about here. Try to draw the slope, might carry me to right there. Now I'm very close. This now would be x4, then x5, then I go here, and the slope will carry me there, and x5, and we're pretty much there after x5. Alright? Now you want to know, how do I really find x1? It's kind of a simple principle. The slope f prime at x naught is, slope is always rise over run, right? So in this case the rise is this, which would be f of x naught. Everybody agree that that's a rise?
Yes, sir.
And the run would be this, just right here. And what is that run? That run would be x naught minus x1. Everybody agree with that?
Yes, sir.
So the slope, assuming this triangle here, this is the triangle I'm looking at. All we're saying is that the slope of the function here is the same as rise over run. So I'll write that down. Rise is f(x naught) minus 0 over run, which is x naught minus x1. Therefore, solving for x1 is equal to, if you look carefully, let me just take the steps. No, I won't shortcut it. And hello, whoever that is, fix that for me, please. Hello. And so x1 is equal to x naught minus f of x naught over f prime of x naught. Everybody see it? So this is how you just do one iteration right there. So the next guess for x is just going to be based on the initial guess minus the function for the initial guess over the slope for the initial guess, and that gives me the next one. Alright, and it would continue in the same vein. That means x of I plus 1, that means the next I is always equal to x, it's always equal to x at I minus the function at I over the slope of the function at I. Alright, so this is essentially the fixed point form. Now note what would happen here. What if I had picked a value right here as the initial guess? It would have thrown me probably, I'm going to change color. Everybody clear on what's happening here?
Yes, sir.
Now let us say I picked another value. Say my value was x naught had started I'm going to duplicate this slide. No, I can't. Alright, I'm going to just keep it as is. Let's create a new one. So what I'm saying is, now let's say I'd started my function, my x naught, here instead. Okay, right here instead. This was my original function. My first guess would have thrown me, based on the slope, about there, that would be the slope. Would have thrown me, oops, let me clean that up. Let me try again. My first guess, let me change color also, so you're not confused it with the other items. No, I don't want to use that color. Let's use red. So my first guess would have thrown me here. Everybody see that? And then that would have thrown me slope that would have thrown me here, and then that would have thrown me to my final answer, close to my final answer. That would be the final one. So what would have happened if I had picked a value a little over to the right? You realize that I would have converged on another answer. So I would have picked a point over here because I would have wanted it to converge on this answer, and it would have thrown me over here and converge on another answer. What is that?
Yes, sir.
In fact, sometimes, let's say you only have one root, your iteration can actually can carry you off into outer space, put it that way. Okay, the root might exist, but it doesn't even go toward that root, it carries somewhere else. I'm going to do some animations to show you that happening. Alright. So let's go back to where we are. Fixed point. So that's Newton. So here this is the same expression that I just showed you. Right? And here it is for any other step. And we just do the same thing until it converges. No different. Now let us go back to the website that we used before. And let's go through it again.
So wait, sir.
We're going to look at some Newton's method.
Writing the.
Go ahead. Wait,
just ask you one question. Yeah, in writing the algorithm, if the function have several other roots, the algorithm will tell that you will have to write a procedure in the algorithm to search for the others.
Right. Well, the algorithm, an algorithm can only find one root. So, because the end of an algorithm says, so you'd have to pretty much have you'd have to have a, you could say, you'd have to have a super algorithm that calls on the Newton method, but starting at different initial points. So you start at a certain point, you find the root. Then because you're not sure it's the only root, you call on the method again, starting at a different point, and find the root. And you may do that, let's say, over a range. So let's say you want to find all the roots that may exist between 0 and 10. Okay? All the roots that exist between 0 and 10. So what you do is you may say, alright, my initial guess is 1, or let's say my initial guess is 0, and I see where Newton-Raphson finds for the answer, and then after you find that answer, then you go initial guess being 1, and then find where it gives for the answer, and then you find where initial guess is 2, and find where it sends you for the answer, and then find where initial guess is 3, and so forth. Go all the way to 10. Now if you go from 0 to 10, and every time you get the same answer, then you can assume it's the only route in that range. Understand?
Yes, sir.
Where you made x naught or x sub 0, you made the first guess of your iterative routine change at a certain increment, and in all cases you fell back on the same route, and you can assume that's the only route. In fact, you could have said I'm trying to find all the routes between 0 and 10, and when you plug in the value 1 or 2 or 5, it gives you an answer at 100, because you can't force Newton-Raphson to remain bounded. You can say where you start, but you can't say where it ends. Okay? The open methods, you have no control over where it goes. Okay? The function determines where it goes. Okay, so let's look at some Newton's methods here. Please, so now I did the whiteboard to show you exactly the procedure. So now when you see the animation, it should be clear on what's going on. First case. This is a single root case. So this is everybody see the projection, and you get to your answer relatively quickly. Alright. Let's go to another one. See, so here we had convergence. Another case. Matrix point. Now look at this case. This is a root. You're going to be surprised. You'll never get to the answer. It's going to take forever. Well, kind of getting there. Ah, we got there. Next one. The answer is 0.2, and it's kind of approaching it, but taking quite a little while to get there. Here's an issue. Remember, in the iterative procedure, we said one part of your normal iteration procedure is that you're supposed to determine the slope of the function at each iteration to see if the slope of the function is approaching 0. If the slope of the function approaches 0, then your answer is 2 roots. That is, if the slope is 0 and the first derivative, the second derivative, first derivative is 0 and the second derivative is a positive number, then we know that it's approaching 0. Then we know that it's 2 roots that exist there. Or we could say it's a quadratic, for example. You could also have the slope approaching 0, but it's a cubic function. In that case, the second derivative also would be 0. And in that case, it's actually 3 roots. But we're not going to go into such complexity. Alright? Let's look at the third case. Now, look at this. We're going to start here. Seems clear. Shouldn't have any problem. This is close to the problem I just did, where we kept going around and around. Right? Alright, let's look at the other one. So this is close to the one I did on the whiteboard. So here's a case in which we have no root, but the system doesn't know that, so it's going to keep looking for it. Okay, and it's going to just keep going in this endless loop. This is why when you're doing iteration, you have to have a maximum number of loops, after which you say the root does not exist. Okay, or in a case like this, this is a third order polynomial, so there a root does exist. Eventually this line is going to curve back down out here, but the main problem is that the initial guess of the root is at a location which would cause the iterative procedure not to converge on the answer, which kind of goes back to what Judan is saying. What if it goes back to what Judan is saying, that you may have to have a set of loops that say, okay, not finding the answer, let me start with another initial condition. Alright, till I get to the answer. Alright, so now we're going to do two more. This is going to be an example where you have a root. Anybody know what the root for this is? The root for this is infinity.
It's an asymptote, right?
Yeah, it's going to asymptote to infinity. So can you imagine you decide you want this to find the root? So it's going to try and reach to infinity. And if you look carefully, each x is about a fixed distance. Right? So it's going to take the time it will take, 4, 5.5, 6, and then it's moving at about the pace of 1. So if the root was 100 steps away, it would take 100 steps, but the root is infinity away, so it will take infinity to get to the answer. The point is this, however, the system is not going to let you know that it's not getting to the root. So that's why it's important. You must understand your functions. Okay, don't let the function waste your time, or don't let the code waste your time. You must understand how your physical system behaves. Final case where you have a root, same, I think this was the same as case 2. I'll go back to case 2. No, it wasn't case 2, it was case 3. Same as case 3, but we're going to start at a different location. Here we started at about 1.3. Now we're going to start not at 1.3, we're going to start a little bit more, just a little bit more, 1.4. Everybody say 1.4. I want you to notice. Please notice. This case, first case, read it right here. 1.35. 1.35 I'm going to converge. Okay? Same case, same function, I'm going to start at 1.4. Look what happens. See what's happening?
It's divergent.
It's divergent. Alright. Subtle issues like that. Now believe me, all your numerical software that's out there, these are the issues that they have to grapple with in trying to give you an answer for your system. Okay? Alright, I'm going to just beg you pause, I have to pause briefly. Alright, I'll be back in a second. Please bear with me. Okay, your patience was very appreciated there. Okay, so I'm wrapping up this topic now. Two more methods, secant, and the other one that you really don't need to know, it's just there for information. That's Mueller's method. Okay, so let's deal with the secant method now. Now the secant method, I like it because it's still a open method, but you're actually picking two values at first. So it almost seems like you'll find that it seems similar to the false position method, but it's not exactly the same thing. Alright? The secant method. What the secant method does, instead of actually calculating the slope of a function, what it does, it just uses the last two iteration values, and from those last two values approximates the slope. Okay, and so let me go back to whiteboard. So wait, what does that matter? Bear with me. Everybody still there, by the way? Okay.
Kind of.
Kind of. Alright. Honest answer. Alright, so here we have, just look at what the secant method would have done. Not secant method, false position. So here you have your function. False position would have said, these are my bounds. So let's say I'm going to, between 0 and this location, I'm going to use a highlighter to identify my bounds. Okay, and so my root is somewhere in between here. What it does is it calculates the value here and the value here, and just draws a straight line between them. Straight line between them, right? And then where it crosses this 0 line, that becomes the new bound. This becomes the new bound, right? And what you do is you pick the two that give you a negative and a positive. So this would be a negative and a negative if you pick these two, but this would be a positive and a negative. So you pick these two and you say, okay, this is now my new bound. Find the value here and do the same thing. crosses at a certain location, and you do the same thing. This one actually comes close to the answer. Alright, that would have been what we just learned some weeks back, which is the false position method. Now let us now consider the secant method. You'll see how similar it is to the false position, but appreciate all we're doing with the false position is that you have a bound here and you are always within this bound. Always within this bound. All it's doing is getting narrower and narrower. Now let us consider the case starting again. And our function. Okay, so here's what we do in the secant method. What we do is we initially select two values. They are not necessarily bounds. Okay, so it's not that you have to pick two values. You know that one is negative and one is positive. The two values can be close to each other. For example, so let me give you an example. I'm going to say one value is here. Let's use here value there, and so this would be x0 and x1. Alright, using these two values as a function for one, and this is the function for the other. These two become used to determine the estimate of the slope. So you recall for Newton-Raphson, what we said was x1 is equal to x0 minus the function at x0 minus the slope of the function at x1. What we do, however, is that the next guess, in this case, this is for Newton-Raphson method, the first iterative step. In this case, the first iterative step would be x2, because if I remember, it's 2 that you start with. x2 is equal to x1, that's the previous one, minus, now you'll say the function at x1 over the slope. Now the slope is actually going to be this slope here. And how do you estimate that slope? Rise over run, right? So rise would be this, which would be f of x0 minus f of x1 as rise over run, which is x0 minus x1. Everybody see that? That's what would go here in the denominator. F of x0 minus f of x1 over x0 minus x1. Or written another way, so really just say x2 is equal to x1 minus x0 minus x1 f of x1 over f of x0 minus f of x1. It's really same as Newton-Raphson, but we approximate the slope. So now, using these two values as a slope, and we go here. Okay, and now that we are here, this becomes the x. This is x2, and this is the value here. Sorry, the value here. This would be f at x2. I'm gonna talk, I may write it. Not seeing, okay, one same not see. What you not see? I mean, what are you not seeing? Is it that the screen gone blank? One.
Maybe the internet connection.
Okay. Alright, so you see now, this is now the x2. So what we do now is the next iterative step is going to be, where is x3? What we'd say is x3, oops, sorry, go back. X3 is going to be x2 minus x1 minus x2 function of x2 over x f function of x1 minus a function of x2. Alright, and it would go on the same way. Now note, all you just keep doing is you just keep discarding the last of the two. So now you're going to be using 1 and 2, and then next we'll be using 2 and 3, and then we use 3 and 4, and keep going on and on. And and again, it is unbounded, it can carry you anywhere. Okay, it's similar to false position because it uses two values and it extrapolates to where the function goes to 0, but it's not similar in that false position always closes your bound. Okay, but secant doesn't close your bound. Secant always just disregards the second to last one and keeps going. Wherever it carries you, that's where you go. Another thing about secant carries you anywhere. Yeah, the two values that you start with don't have to be the same. Have to be different signs. They can be the same sign. Whatever you get, that's what you work with. Alright, so I'm going to show you a secant animation. So we're going to start with two values. So the 2, and that's the slope that the 2 give. Then we're going to disregard this one, and it uses those 2, and it keeps just using the last 2 till it gets to the answer. Alright, but as I noted, secant can carry you anywhere.
Why not start that over, please?
Alright, I'll go back. There we go. See these two? Those are the first 2, and this is the extrapolation to 0. Note, this point is disregarded for the second. We use this and this. for the second iteration, these two values. And then for the third iteration, we use these two values. And then for the fourth, those two values, and so forth. Alright? Let me jump over the case where the function goes to 0. The slope of the function goes to 0. That's this case. Don't want to use this case. Just want to drive home. So here's secant again, using 1.3, two values. Wow, we got to the answer pretty quickly. So here's what it did. Note, these two values were the initial guess, right? Those two were used to approximate a slope. That slope carried us to this point. Okay? This is now the value of the function at that point, right here. Now what we're going to do is we're going to disregard one of these. That's this one. And we're going to use this one and this one. That's the value of the function here. The value of the function here. So we draw a straight line between the two, and wherever it goes, that's now our third iterative step. Okay, and now we disregard these two, and now we're using this one and this one. So I draw a straight line between both of those, and wherever it crosses, that's now my fourth iterative step. Now I disregard this one and I just use these two. These two are of course very close to the answer. You get to the answer very quickly. Alright? We soon talk about the benefits of the secant method. Got another case. Remember this cube case where we were just looking at way down here and we never got to the answer? Amazing. It actually gets to the answer. Note. You realize it seemed to be haphazardly searching all over the place. You realize that? You want me to run this loop over again?
Yes, please.
Yes, sir. Run it again.
So the two first guesses are down here. First guess. Disregard this now. These two. That guess. Disregard that now. These two. And this is off the screen, but it's there. Okay? Moving on. What I want clear to you is that the secant isn't bounded by where you started. Okay, we started here and we go all about the place till we get to the answer sometimes. And you cannot get to the answer sometimes also. Okay. Now you'll note, remember the Newton-Raphson method. If you look at this, the spacing is about the same. Remember it was about 1. So the secant is approximately like the Newton-Raphson in terms of how quickly you get to your answer. Okay, this is the same function as the Newton-Raphson case. and it iterated the same way, except that it's a little tighter space. That means it's not progressing toward infinity as fast. Slightly slower, but not significant to say it's different. Okay, here we go again. Now the first case, so we're at the answer. The first case was, I believe, the same case. No, I don't. Let's see. The first case was this one, right? Oh, the second one. Nope, third one. Yeah, third one was similar, but we started at a different point. Can I get back to the same answer? Alright. So that's the secant method. The last method is the Mueller's method. I'm not going to give you an animation, I'm just going to explain it. Alright. So Mueller's method, everybody should be clear on the secant. You should see this is what I had here. If I go back to the whiteboard, let me recall what I had here. Note, I want you to see the similarity. Okay, look. So for example, this would be, let's say we're doing x3, it would be x3 equal, in this case, don't matter. Here we have it as x naught. You could have used x1 also, it would have switched some things around. Let me write it in that form. So I could have had it this way instead. So let's write it just to be clear. So I could have said x2 is equal to x naught. So I could have made this the case, and then I do the same rise over run. It don't matter. Okay, both of them would give me the same answer. So let me put the x naught there. And then you'll see it. So in this case I'd use 1, x1 right here. Okay, as I said, both of them will get you to the answer. Let's look again. So here we have x3 is in the case where n equal 2, then x, this is 2 plus 1, x3 equal x1 minus the function for x1. Let's see if that's what I have here. Oops, sorry, made a mistake. Right, x1 minus a function for x1, then it would be x2 minus x1 over the function of x2 minus a function of x1. Right, so x2 minus x1 over the function of x2 minus the function of x1. Everybody can appreciate it doesn't matter which way the sign goes, because it's the same order in the denominator. Alright. So that's the secant method. Mueller's method says you use the last 3 values to approximate the function, and what we do is you assume it to be a quadratic. So instead of saying I pick 2 values, what I do is I pick 3 values, and from the 3 values I fit it to a quadratic function and find out where does the quadratic function cross the x-axis, just using the standard expression for the root of a quadratic function, which is the root is equal to negative b plus or minus the square root of. Everybody remember it? Want to tell me?
Minus, what was it? What's the minus?
What's the minus square root of b squared minus 4ac over 2a?
Good. So that's all it does. So what it does is you pick 3 values, you start with 3 locations, let's say that, that, and that, and then what it does is it says, okay, using those 3 I'm going to fit a quadratic to those 3 points, and with that quadratic find the root, and wherever that root is, let's say the quadratic might be something like this. Sorry, not so pretty, but you understand, you get the general gist. This is a quadratic. Okay, so now this would be the 3 points that you use. So the value at that point, the value at that point, the value at that point, and you disregard this now, and now you use those 3 and then you fit a quadratic to that, and so on till you get to the answer. That's Mueller's method. So it's similar to secant, except secant fits it to a straight line, Mueller fits it to a quadratic. That's all. Alright. So that's pretty much iteration to solve for a function. Just give me 15 more minutes. I'm going to now introduce the last one, the last iterative procedure. Let me end this show. I will keep the ink so that you guys remember the ink is also online. It's on the recording, you know, but I'll keep it for your sake. You're welcome. Alright, so now we're doing optimization. Now for those who did the course called Operations Research, you would have learned optimization, but for linear systems. Remember this course started with solution of linear problems, and Operations Research would have been doing optimization for a linear system, a linear set of equations. Okay, so when we talk about optimization here, we are thinking of optimizing nonlinear systems, just like how you needed to solve nonlinear systems just now when we were doing iteration, fixed point, bisection, root, fixed position, or false position, Newton, or secant, or Mueller's. Those procedures are for nonlinear functions. And sometimes your concern is not to find a function value, but to find the best in either a minimum or a maximum for a function. Okay. So there are 5 methods, and we're going to just go through those 5 methods quickly. There are some animations for them also. Alright, so we look at those animations. So quickly, what is optimization? By the way, note, optimization is also an iterative method. We are still going to have to go through loops and so forth. So it is iteration, but it's just traditionally the topic called iteration really means root finding and fixed point finding. That's what iteration used to mean. Or solving non-linear problems. Now optimization, what we're calling optimization, is solving the minima or maxima for non-linear problems. That's what we're doing. For those who did operations research, that entailed solving the minima or maxima. It's not really minima or maxima, but finding the best case for a linear system. You should all appreciate that a linear system does not have minima and maxima. Straight line does have a maximum or a minimum. Everybody clear on that?
Yes, sir.
So it's not really the same. All it is that you have a bounded region, a space, and you want to find where, let's say you have 4 corners in this space. One of those 4 corners is the best or the worst. Alright? So that's what optimization from the linear perspective looks at, not minima and maxima. Minima and maxima, for those who forgot, is any curving function that peaks. We call that a convex, or sinks concave to a place where the slope goes to 0 and then it starts to rise or starts to fall. It was once rising and then it gradually starts to fall, where the instant where the slope, I know this seems plain and obvious, but I'm not taking anything for granted, so everybody know everything. So I know you can appreciate that. So this is what a minima is, the location where the function starts to go down. That's a maximum, and this is a minimum point where the function starts to rise, coming from this direction, and the point where the functions, well, it doesn't matter which direction. The point where a function starts to rise is a minima, and the point where a function starts to fall is a maxima. Okay? One thing we know about minima and maxima is that their slope is always 0. You do have a case where the slope goes to 0 and it's not a minima or maxima. That's called a saddle. Hold on. This is a saddle. Let's draw an example. It's like a saddle here. Like in this case, the slope goes to 0. Okay? So what is optimization? Generally speaking, I'm not talking for engineering, just generally, it's the process or act or methodology or strategy for making something perfect, functional, or as effective as possible. Okay? And it's a procedure. That means it's a procedure. So optimizing means you do something to make the system better. Right? In engineering, it's a procedure in finding the parameters that result in a best, not at, but a best possible output for a function. And best is defined either as maximum or minimum. It all depends on your scenario. For example, if expenditure is the function, then minimum might be best. But if income is the option, net income that is, then maximum would be what we call best, right? So it depends on what the scenario is. You will note that because optimization, as we are teaching it here, is an iterative procedure. Remember, it's optimization of nonlinear systems or functions. Because it's an iterative procedure, it actually involves the exact same considerations for the previous topic. Alright? You need to optimize something, you need to bound it or do an initial guess. Past experience can help you to assume where the optimal point might be. Knowledge of a model is important. Pretty much the same thing. All that is changing is what you're trying to find. You're trying to find a minimum or maximum. You're not trying to find where the function is 0. And note, everything here is the same as with iteration. The only difference or the only added matter is the saddle. Okay? A saddle is not a true minimum or a maximum. Not a true minimum or maximum. Minimum or maximum. Alright? But all these considerations here are the same that were in the iterative procedure spoken of in the previous chapter. You're bounding, if you use you have bounded methods and you have open methods, just like you have from the previous chapters for root finding. Okay, so minimum or maximum finding, you can bound it or you can have open methods. Okay, closed methods are always sure if you know that the answer exists and it's only one answer, or you may not even sure if there are more than one answers. But especially for optimization, knowledge of the fact that there's one answer in the bound is very important. And so we have bounding, and which is always preferred when you can bound your system, because you know you'll get to your answer. And an open method usually gets to your answer very quickly. But sometimes if the function is a haphazard, not so clear function, then your open method, if it didn't start it at the right location, can throw you away from your answer, just as it did for the previous section. Alright? So that's pretty much the same as the previous sections. Also, the same procedures apply when you're writing the code. You must say don't go over 100 or 1,000 or 1,000,000 iterations. It all depends on what you're looking for, right? That means if you reach 100 iterations, say, boy, we're not reach an answer. So stop the procedure and report that that no solution can be found. You must always check that your second derivative doesn't go to 0. Please note. Remember, when we're doing regular iteration, you're supposed to check that the first derivative doesn't go to 0, or check whether or not your first derivative is going to 0. Do you recall, if your first derivative is going to 0 while you're getting to your answer, what does that mean? That is for the root finding. Everybody recall? People are zone out. Some people just asleep on me, man.
2 roots?
2 roots, right. means two roots. It doesn't mean that no root exists. It means that it's two roots. Now in this case, where we're doing optimization or finding the minimum or maximum for nonlinear systems, you don't check for the function first derivative going to 0, you especially check for the second derivative going to 0. In that case, it means, if the second derivative going to 0, it means that the minimum or maximum that you find is really not true. It's a saddle, that's all. Okay? So while for root finding that derivative tells you it's actually two answers there, in this case it's telling you that there is no answer there. Okay? And you should always have your error limit or your convergence test. You should also check to make sure that you are really at a minimum or maximum. How do you check? How do you check? Look at the final statement. Simple way to check. You pick three values. The middle value must be your answer, and two other values must be to the left and to the right of the answer. And you should plug those values into your function, and the two outer values should always be both either higher or lower than the middle value. Okay, and when that is the case, then you can say, okay, it's a minimum or a maximum. Alright? Golden section is the first type of minimum or maximum. It is just like it's similar to bisection. Alright, it's bounded. You need to, you pick it because you know that the answer exists between the two. Alright, called the golden section. I'll quickly describe it. There's a number called the golden ratio. I'll explain what that means soon enough. And then there's another one called the regular falsy. Called the parabolic. And the parabolic is similar to regular falsy. So what I want you to appreciate is that these methods, the methods for optimization, have analogies with the methods for root finding. Okay? Please note I say root finding. So there isn't an analogous method for optimization that goes with fixed point finding. Okay, but you have it for bisection, you have it for regular falsy, and you'll also have it for Newton-Raphson. Alright, and here we go, Newton-Raphson. Okay, so the Newton method, there's a Newton method for optimization also. And there could be a secant method, though I'm not really showing you the secant method. Alright? So, these are the important methods for one-dimensional non-linear system to find the minimum and maximum. Now I'm only going to go through the golden section and then we call it a night. Okay? Everybody with me still? Kind of?
Yeah, man.
Okay.
Yes, sir.
Yes, sir, but could you explain what you mean by one-dimensional?
Alright. What do I mean by one-dimensional? Good question. Let me go to slide. So you would have noticed, if you may have noticed that there's a section called multidimensional optimization. So I'm not discussing that as yet, but let's do this first. So we have here is how would I? All right. Multidimensional optimization is a case in which you have a two-dimensional space. I want to erase this soon, but just to that shouldn't have happened. Let's do that over again. So here's our multidimensional space, and I could have something similar to the MATLAB logo. I think Octave kind of use the logo too. So what we have here, these lines represent, let's say, values of x, y, and z. This would be lines of constant y, this would be lines of constant x. So the maxima would be here. This is a two-dimensional case where you find the maxima. Alright? I've a case for, let me give you, if you were to project this space on the ground, it may be like a shadow. It might form a shadow like, let's see, might form a shadow. Yeah. So it might form a shadow like this. Point goes to that curve, and this goes right here. The shadow on the ground. Hope everybody getting what I'm saying. This is a shadow, okay? And so these lines would project as some shadows on the ground. Those are the constant X lines, and these will be constant Y lines on the shadow. Everybody see the shadow? And the maximum, let's say, might be here. That means for this X, for this Y, and for this X and that Y, this is the maximum value of the function in this region. Alright, so that's what we mean by a multidimensional case. Now you don't have multidimensional when you're doing root finding. Alright, you don't have a value for a function. A value is one value. You can have a value, how should I say this? Okay, imagine this function, imagine that sheet, I'm calling this a sheet, or this function here, a little lower. Okay, and I say, when is this function equals 0? You should all appreciate that this function won't be equal to 0 for an x or y. It actually would be equal to 0 on a line. Or imagine moving x and y a little higher. So that means the x-axis is here, the y-axis is there, the x-axis is here. So this actually cuts the plane, the xy plane. So that's where the function would be 0. So that function is not a value. Okay, because it's going to cut through the xy plane, and there would be a line representing where the function cuts through the xy plane. So because of that, you don't really talk about root finding with multidimensional problems, because when you have multidimensional problems, you don't necessarily have a value of x or y where the function equals 0. What you have is a line of x and y where the function equals 0. But you can speak to minimum and maximum for both single dimensional and multidimensional problems. That means there is a value when you have a single function or a single dimensional case. This is a single dimensional case. There is a value of x that gives you a value for the function, and this a value is the max of that function for this range of x. It's a value. Similarly, it could be a multidimensional case like we have here, where for this range of both x and y you still have a value. Okay, a value for z, or the function, the value of the function at x, at the maximum value for x and y. Alright, it's a lot of talking. I hope it makes a little sense. Did it make a little sense? Please tell me whether it makes a little sense.
Yeah, I think I understand.
Okay, let's get back to the golden section. So the golden section principle is this. Left out a blank slide here. So what we have here is a Alright, so here we have a case where we have a maximum somewhere. Golden section says, okay, you're going to bound it first, and you must know that your bound, you must know that your bound bounds the maximum or minimum value. Okay, so I have here x0 and x1. The next thing I want to do is bisection. It says divide the space in two. I'm going to show you. Let's do that and see if bisection will make sense. Divide the space in two. Now when you divide the space in two, you have this value, that value, that value. How do you know whether or not the maximum is in this region or if the maximum is in that region? This is the big issue. We just don't know how to determine that. Anybody can think about a way in which you can use you, but based on this value, determine where the maximum is? Alright, I'm not wasting no time. It's not possible just by using one value. You need two values to do it. Two in-between values. Let me give you an example. This would seem to suggest, because this value is lower, this value is higher, then you say, oh, it's probably on this side. But the function could have looked like this, you know, in between. Right? And so the answer is really on this side. And you realize, just picking this one value, both of these functions give you the same answer for this one value. Doesn't really. So you have this function g of x, and you have this function f of x. And you realize that if you were just looking at those values, both g of x and f of x give you the same thing, but you realize that the maximum on this case is here. For f of x, the maximum is here. That's to the right of the middle. And for g of x, the maximum is to the left. So you need another way to be able to judge, to be able to judge where the maximum and minimum is. So what we do is this thing called the golden section. It's a special number. It's a special number that I'm going to divide the space into two bounds. One here and two values, one here and one here. This is 0.6. Let me give you the exact value. Coming. Zero point six 1.618, I believe. Let's see if I can find it. Alright, 0.618. It's a special number. It's called the golden ratio. We'll talk about what's so special about this golden ratio. Everybody see it? Golden ratio. Okay? Let's go back to where we were. So 0.618 right here. And from here to here is also 0.618 of the full range of x1 minus x2. Okay? Of x1 minus x2. Now what we do, note, let's consider we're looking at the f of x function. Here we go. What we just did is we found two values in between these two cases, and what we say is I want you to note carefully, when we look at these two values, we have to discard, we're going to decrease our bounds. Alright? So the question is, should we make our bounds this side? So that should we make this our new bounds? That's the x naught side. Or should we make this side our bounds. This is the x1 side. What would you do? And what is the criteria for deciding where would the new bounds be? It's just like in bisection. In bisection, you split it in two, and you say the new value, is it positive or negative? And if it's positive and the other bound is negative, then you pick them. Or if it's not that case, you just always pick the bound that makes one positive and one negative. But that's not the case here. So what we want to do is, do we now make the new bound this be the minimum and that be the maximum, or do we make new bound this be the minimum and that be the maximum? Which one should it be? We're looking at the f of x function. It's obvious from the graph which it is, but you're going to have to now tell me the basis. So we're looking at the f of x function. Do we pick the yellow range or the green range? Guys, yellow range or green range?
The green range.
Okay, what's the criteria that would tell us to pick the green range? No, but suppose you don't know the maximum is there. Suppose you can't see the full graph. You don't see the line. You're not seeing the line. You only know the points. That means if I deleted this line,
well, f of x1 is higher than f of x2.
okay, let's write out the labels so you can tell me what you call x1 and x2. So I'm going to call this.
Sorry, I mean x.
Let's call this.
X0.
Let's call this 2 and x3. So you say 2 is greater than 3?
No, sorry. X1 is greater than x0. Stop it.
Okay, x1 is greater than x0, true.
F of x1 is greater than f of x0. So it means that the maximum will be closer to f of x1.
Suppose this line had maximum like this and then went down. And delete that. Let me do that again. Mute whoever may I hear. Mute that for me. Let me tell you who is that? What I'm hearing. Okay, thank you. Suppose we know that the maximum is somewhere here now. Alright, suppose the function look like this. Talking the same f of x now. Franklin.
So you insert function like that, then that means
Yeah, I'm looking at it.
x2 going to be on it, on the
So
board.
x2 would be here still, right?
Yeah.
That's where x2 would be.
So you just plug in x2 and the function and compare it to the others.
Alright, the principle is simply this.
Which one is the highest one?
What we do, we're looking for a maximum, right? Everybody clear? We're looking for a maximum. So
Yes, sir.
the principle is this. Of these two values, which one is larger? Okay? whichever one is larger of the two, then you pick the range that will make the larger one in that range. Okay? So I'm going to erase what I just, hold on. Let me erase what I just drew.
Sir, for the yellow bone, should that be x1 minus x2 still?
The yellow bone is between x0 and x2.
In bracket you have 0.6.
Oh yeah, it should be x0 minus x1, sorry. It should be 0 minus 1. 1 minus 0. Alright, both of these should be 1 minus 0. Let me fix that. Am I clear? Let me just confirm it. You should say okay, so the distance here, or this length from here to here, sorry, I'm trying to use something that you can see, from here to here is 61.8% of from here to here. Alright, and from here to here is 61.8% of from here to there. Alright, Orlando?
Yes, sir. I understand.
Okay.
So,
continue.
so if that's the case, then how would you find x3 and x2 if you don't have a graph, for instance? Because you can easily see it based on a graph. But
I'm going to take away the graph. I'm going to take away the graph. Good. Let's look at both cases. I'm going to take away this graph also. I'm going to, alright, let me just do the f of x case first. So what I did is I found the function, and I found that this function, the value here and the value there, and I realized these two values, this one is a larger one. So because this one is a larger one, then my bound must be somewhere here. Look at it this way. Remember, it's only one maximum in the system, right? Everybody listening? You only have one maximum in the system.
Yes, sir.
So it is impossible. It is impossible for this system to go above this point. It starts here and then go above the point and come back down. If it went above the point, that means there's a maximum over here also, and that gives you two maximums. The only way in which there could have been a maximum to the left is that there would be two maximums in the system. But remember, you only use this where you have one maximum that's known or one minimum that's known. So let's take away this. So from you do these two and you see that this one is greater than that one, then you know the maximum must be on the right hand side. And so you make that now the new bound. The maximum could be here, you know, or it could be there, we don't know. Okay? What about the case where I had the g of x? In the g of x case, this would have been, this value would have moved higher. Okay, and then we would have said we know that it will have to be on the left hand side.
Because x3 would have been higher than x2?
Right, because x3 would have been higher than x2.
Oh, okay, alright.
Okay. So after you do that now, then it actually starts becoming a one value solution per iteration step. So for the first case, I had to find 2 locations, but from that I keep just finding 1. Let me explain what's happening. So what I'm going to do now is I'm going to find a value for x4, and this value for x4 is such that this region here, from here to there, what is the region, is again 61.8% of x1 minus x3. Everybody see that?
Yes, sir.
And it also turns out, this is why we call it a golden number, that from here to here is already 61.8% of x1 minus x3. Let me just do the proof on an Excel slide. To start with Pablo, you are the only one who can't see the current slide. I'm sorry. But it's being recorded, so don't worry about it. Something is wrong with your, like something is wrong with your connection here. Everybody is seeing the slide, right? Yes. Sorry, Pablo. Alright, so here's the case. 0 and 10. Alright, Pablo, use your imagination. Alright, so I'm going to pick Hello. Brandis. Mute. Thank you. Alright. So what I'm going to do is I'm going to pick a value here that's 61.8% toward the 0. So it's going to be 0.618, sorry, yeah, 0.618 times that value minus this value plus 0. No, plus 10 minus, sorry. Let's say this minus, good. And in this case over here this value is going to be equal to this side plus 61.8% times d minus a. Alright, now here's why we call it a golden number. Let us say I decide to make this the new bound. That is, make this value one side of the bound and 10 remains the other side of the bound. Okay? When I do that, I'm going to now copy these two formulas down. Note, you realize that 61.8% to this side turns out to be the same number here. See the value came back here? The value I had here came back here. Alright, I'm sure some of you didn't get that, so I'm going to do it again, one more stage. I'm going to imagine that my new bound is this value still, and this now becomes my new bound. So I'll go here, that's now my new bound, and this will be my other bound. And I'll copy down these formula again, same formula. You realize this value is still there. It's a special number. Alright, let me still use this bound. Let me use this bound, and now this is going to be my new number. So you know the 61.8 have to go out. This 6.18 has to go away. I'm going to copy this down. When I copy this down, one of these numbers will still be there. See? This one I said. I'm going to make all of these to 2 significant digits. So we are clear. So I'm always just going 61.8%, and you see this number repeats itself. See, this one is there. So let me go back to what I'm saying here. So I started between 0 and 1. These two, 2 and 3, were my 61.8% from the two sides. If I pick 3 as my new bound, then 2 is already 61.8 from 1 using 3 as my new bound. All I'm now going to do is find the other 61.8. Okay? And when I find the other 61.8, now I must ask myself, what is going to be my new range? Will my new range be between 3 and 4? That's from here to here. That's a 3 to 4 range. Or should my new bound be between 2 and 1? Alright, the 2 to 1 range, or the 3 to 4 range. How do I decide? I find what the value is at 2, and I find what the value is at 4. Whichever one is higher, I pick the range such that the one that is higher is inside that range. Okay? And when I do, so let's say I find out that the value at x4 is higher, then from 2 to 1 would become my new range. And then I have to do 61% from 2. Let me change that color and imagine that to be now here. So now my two ranges are either from here to there or from here to there. How do I determine which one is the one I pick? Looking at this value and this value, I find the one that is highest, and when I find the one that is, I think it dropped out. Anybody there? Me. Who's hearing me? Nobody is hearing me, right? Okay, let me just log out and log back in. Okay, my internet dropped. Okay, just picking up where I left off. Everybody seeing the presentation, or you should see it in a minute. So what we're saying is, tell me if you're seeing. Okay, so here we were right. Here we were saying, we had said the bound x1 to x2 now would be where my bound is. This location would have been one of my golden ratio locations from the previous iterative step. No, this one is what I calculate for the new iterative step. Alright, and then I look at both and I say which is largest. If this one is largest, then my new bound is going to be this and that, so that the large value is within the bound. If this one was larger, then the new bound will go from here to here, so that a larger value again is within the bound, and so on. Alright, so that is just the general procedure, or explicitly stated. Hold on. Here it is. So explicitly stated, we identify the two. This is just for the first case. You identify the new two values. You have your upper and lower bound. You identify two values within the bound based on the golden ratio. Okay? Everybody understand the two values. Now you calculate the function of the two values. Alright? If, for example, the positive function, that's the one to the right, we call the positive the one to the right, okay? Left. Okay, good. Positive is the one to the right, and the negative is the one to the left. So if the positive, let me just draw it right here, just so we're clear. These are our bounds. So you have XL, you have XU, that's a lower, upper, then we can call this X minus, and we call this one X plus, okay? And all this is saying is the function of X plus greater than the function of X minus, then the new lower bound, that means if this value is larger than, sorry, use the arrow. So if this value turns out to be larger than that value, then the bound should go from here to there. So all we're saying is now make the new lower bound X minus, vice versa, or if however this is a larger value, then we make the new upper bound x plus. Okay, and you just keep doing that until the two functions are almost the same. When the two functions are almost the same, then we say we are at a maximum. Okay, if it was a minimum, it's quite clear. You would just simply say if this is less than that, and everything else will be the same, or if this is greater than that, then this will be the same. Alright, so you have to know when you're doing the golden section search, you have to know if it's a minimum or maximum that you're looking for, and you must know that it's only one minimum or maximum that is between or within the bound. Alright, that's the golden section. So you have to find the initial guess, just as for the bisection method when you're doing root finding. It's a very important step. If you do know that it's a continuous function and you know that the bound exists and you know that the maximum exists, then once you bound the thing properly, you will always get to the answer. Note, convergence is slow, but because it's just as fast as each step cuts the system by a fixed amount. Okay, discontinuous problems can pose problems. It's the same as it was before for root finding. Make sure you understand your system. If you do not understand your system, then the computer will tell you rubbish and you won't understand what it means. Alright. We'll stop here for the night. Next topic, the next version would be regular falsy, or parabolic, but parabolic is really again like an upgrading of the golden section, just like our regular falsy was an upgrading of the bisection method. Alright, I won't go into any of the other methods. It's there for your reading. It's there for your reading. Alright, but next week we have to deal with the multidimensional methods. They're very critical, and it's not abnormal for you to have a multidimensional problem where you have two independent variables and you want to find out where the maximum exists. It's like finding the top of a hill on a map. Okay, not the top of a line, but the top of a area. Or a valley, the depression in a valley. And I use the analogy of hill and valley because that is going to be very important for us to appreciate the strategies for determining minima and maxima for multidimensional systems. Alright, that's it for the night. As I said, the session is recorded, even though I was kicked off a little. That doesn't impact on the recording. Alright, so by tomorrow hopefully you'll see it. Alright guys.